Hi everyone. We are from National Defense University of Malaysia, and we would like to present our project titled "Development of Lifejacket with Integration of Passive Visual Signaling Feature." So, the focus of our project is to improve the visibility and effectiveness of life jacket during search and rescue operations by integrating a passive signaling feature that doesn't depend on power sources. So these are the flow of my presentation. So first I'll start with introduction and problem statement, followed by the literature review and methodology, result and analysis, conclusion and recommendation, and finally I'll end with references and awards. In maritime emergencies, one of the biggest challenges for rescuers is visibility, spotting survivors in the vast ocean. From a helicopter's view, a survivor's head appears as small as a coconut. Common signaling tools like CDI, flash, and electronic devices have limited duration or battery life. Equipment such as EPIRBS or SARTS only indicate the general area, not the exact location. Therefore, there's a critical need for innovative survival equipment feature that can provide reliable passive visual signaling, enhancing visibility without depending on external power. So this need forms the basis of our research. Based on that problem, studied explored three key questions. First, what are the limitations of current life jackets and signaling devices? Second, how can a passive visual signaling feature be effectively integrated without compromising functionality? And finally, how does this integration affect the visibility and performance of life jackets during search and rescue operations? To answer these three, ma, the research had three main objectives. First, to analyze existing life jackets and visual signaling devices. Second, to design the prototype life jacket with a passive visual signaling feature. And third, to evaluate its performance through several practical tests. This project contributes in three major ways. First, improvement of maritime safety standards by offering a new safety feature that enhances visibility. Second, economic and practical benefits as it uses simple, low cost materials requiring minimal maintenance. And lastly, enhancing survivability in maritime disasters by increasing detection chances during rescue missions. The research aims were to analyze current gaps in life jacket designs and to design a new prototype integrating PVSF, and lastly to test it under controlled conditions for performance and practicality. The scope covers designs, development, and evaluation of the prototype using ADDIE model, focusing on real-life applicability for maritime users. So this slide shows the three main phases of research flow. First phase, analyze, studied existing life jacket and signaling devices, identifying the best materials and design suitable for integration. Design and development, the prototype was developed using the ADDIE process, beginning with a CAD sketch and ending with an actual form-filled life jacket that includes a deployable deflective streamer. Phase 3, evaluation. The prototype underwent several tests including buoyancy, durability, deployment, and visibility tests to measure its real-world functionality and effectiveness. So, from the literature review, several key areas were explored. International SOLAS standard for safety at sea, current life jacket types and visual signaling devices in the market, limitations of radio wave signaling tool like EPIRBS, and the uses of retroreflective and fluorescent materials as passive signaling options. Studies also revealed that search and rescue helicopters operate at altitude between 20 to 100 meters, which guided my prototype's visibility testing distance. These reviews formed the foundation for my design concept. So, the ADDIE model was applied throughout this project. So, analyze, identify problems with current life jacket and define design needs, design, plan and sketch the prototype using CAD, selecting suitable materials, and construct the prototype and integrate the PVSF system. And fourth is implement test in controlled water condition for buoyancy, visibility, and reliability. And finally, evaluate, assess the test results, refine designs, and compare performance to existing products. So this structured model ensures that each stage of development was systematic and measurable. From this analysis stage, several materials and types were compared. First, form-filled life jacket were chosen because they are reliable, low maintenance, and maintain consistent buoyancy. For the passive visual signaling feature material like nylon, plastics, and polyester were assessed. Among them, polyester was selected because it's durable, resistant to degradation, and provides strong color visibility. Although it has low buoyancy, it was solved by adding foam strip to keep it afloat. So the prototype was designed with a focus on enhancing visibility through integration of reflective materials and phosphorescence edges. It used closed cell polyethylene foam for buoyancy and a polyester streamer for signaling. The streamer was stored in a front compartment and could be deployed using a ripcord mechanism. During pool testing, the prototype maintained its structure, buoyancy, and attachment integrity, proving its practicality and reliability for use in emergencies. The first test measured buoyancy performance. The life jacket successfully supported individuals up to 80 kilograms while maintaining a face-up position, crucial for survival. For PVSF, the streamer initially sank without foam, but once a floating mechanism was added, it remained visible on surface even in motion. This confirms the effectiveness of foam-assisted PVSF design. Next, the durability test showed no visible degradation or color fading, indicating high reliability under normal conditions. The deployment test evaluated the ripcord mechanism. Deployment took between 30 to 34 seconds, with success rate improving from 97% to 99% after repeated trials. This proves the system is quick, efficient, and dependable for real world use. So finally, the most important test is visibility test. Using a drone at various altitude, visibility was tested from 20 to 100 meters. The results showed At 20 to 60 meters, the prototype was clearly visible, scoring 4 to 6 on the scale. At 80 to 100 meters, visibility improved from not visible to barely visible, which is a significant improvement. This means the PVSF successfully enhances detection range, particularly for aerial search and rescue teams. To summarize the findings, first objective successfully analyze the existing product and identify limitations. Developed and second objective develop a reliable prototype integrating the PVSF. Third objective were evaluated and confirmed the improvements in visibility, buoyancy, and durability. The results prove that integrating a passive visual signaling feature enhances the life jacket performance in search and rescue scenarios, offering a low-cost, power-free solution for maritime safety. Limitation recommendation. Of course, there were several limitations. First, testing environment. Done in a pool, not open sea. Future studies should test under waves, currents, and weather conditions. Second, material selection. Polyester need foam to float. Future studies could explore self-buoyant materials. And third, hybrid feature. Future models can combine passive and active signaling for greater effectiveness. And fourth, funding limitation, financial constraint affected prototype improvement. And finally, industrial collaboration. Future projects should work with regulatory bodies and manufacturers to make this feature part of official life jacket standards. Lastly, I referred to multiple credible sources, including IMO SOLAS guideline, maritime rescue studies, and recent research on signaling materials and safety equipments. So this project also has been recognized for this innovation in maritime for its innovation in maritime safety, which motivates me to continue improving it for real world users. Thank you very much for your attention. That's all from us.